After a detailed analysis of Legendre polynomial and Bessel function, now we are going to discuss a very important polynomial which is actually Hermite polynomial. You know, Hermite polynomials are actually the solutions of Hermite differential equation. So first of all, we will see what is Hermite differential equation and how we can solve it in series. Actually, the series solution of Hermite differential equation gives the concept of Hermite polynomials. So let us see what is the Hermite differential equation and its series solution. In fact, Hermite differential equation is given in this manner. You can see here. This is d2y dx square minus 2x dy dx plus 2ny equal to 0. This is just a second order differential equation with variable coefficient. You can see here. In fact, in this equation, this n is a parameter. Now, after this, knowing this differential equation, that is Hermite differential equation, we want to solve it in series. You can see the series solution of this equation may be written in this manner: y equal to x raised to the power m times a naught plus a1x plus a2x square plus so on. In fact, here this a naught is not equal to 0. And in compact form, you may write this expression in this way: y equal to summation over k 0 to infinity akx raised to the power m plus k. Now you know we will find the derivatives dy dx and d2y by dx square from this equation 1, and then we will substitute those values in the Hermite differential equation which is defined in A. So now let us find these derivatives. You know this dy by dx will be what? You can see this will be simply summation k 0 to infinity m plus k akx raised to the power m plus k minus 1. And again, when you will differentiate it with respect to x, you will get d2y by dx square, and that will be equal to summation k 0 to infinity m plus k times m plus k minus 1 times ak x raised to the power m plus k minus 2. Now we will substitute the values of y dy dx and d2y dx square in the equation A. See this equation A here, and let us substitute the value of y dy dx and d2y dx square which we have defined just now. So you can see d2y dx square, this will be equal to this much as you can see here, and the second term is minus 2x dy dx, and we have obtained dy dx here. So put the value of dy dx here, and this will be the term. Now the third term is 2ny, and y has been defined in this manner. You can see. So this is plus 2n summation k 0 to infinity ak x raised to the power m plus k equal to 0. Now we will simplify this equation to some extent. The first term remains at it. You can see here there is no change in this first term in this step. And now let us multiply this second term by this x. So after multiplication, the x will have a power m plus k, and in the last term there is also x raised to the power m plus k. So we will take ak times x raised to the power m plus k as a common factor, and the remaining terms will be minus 2 k 0 to infinity and m plus k minus n ak x raised to the power m plus k equal to 0. Now after getting this equation, we will write the initial equation and you know the initial equation is actually a quadratic equation having two roots. So to write the initial equation, what we will do, actually we will equate to 0 the coefficient of lowest power of x, and you can see this series, the lowest power of x will be obtained when k will have lowest power, that is k will be equal to 0. So when we will put k equal to 0, in first term x will have a power m minus 2, and in second term x will have a power m. So x raised to the power m minus 2 is the lowest power term, and so its coefficient you can see is m plus k times m plus k minus 1. But to get the lowest power of x, we have to put k equal to 0. So this will be simply m times m minus 1. So you can see here that this coefficient is m times m minus 1 into a naught, and that is equal to 0. But as I have mentioned earlier that this coefficient a naught is not equal to 0, so definitely m times m minus 1 will be equal to 0. So m times m minus 1 equal to 0, and this will give actually two values of m. You can see either m will be 0 or m minus 1 will be 0. And if m minus 1 is 0, then m will be equal to 1. So I have mentioned here that m has two values. First one is 0 and another is 1. Now, to get the value of the second coefficient, that is a1, we equate to 0 the coefficient of the next lowest power term, and that is x raised to the power m minus 1 when k is equal to 1. You can see again here, when k will be 1, then in the first term the coefficient of m minus 1 will be what? That will be m plus 1 into m into a1. So this is m times m plus 1 into a1 equal to 0, and from here you can see if we put m equal to 1, then neither m nor m plus 1 is 0, so definitely a1 will be 0. So you can say that when m is equal to 1, then a1 will be equal to 0. But if we take m equal to 0, then there are actually two possibilities. In this condition, when m will be 0, then a1 may be 0 or a1 may not be 0. So we will see later on these possibilities after the solution. Now, after getting these two values from the roots of the initial equation and the value of a1, now we will write the recurrence relation to get the general equation to evaluate the other coefficients. And for getting the recurrence relation, you know, we actually equate to 0 the coefficient of general term, that is x raised to the power m plus k. And you can see in the first term x has a power m plus k minus 2. But if we want to make this power m plus k minus 2 equal to m plus k, definitely we should replace this k by k plus 2. So in first term, k will be replaced by k plus 2. And in the second term, already there is x raised to the power m plus k. So there will be no change in the second term. So you can see the coefficient of x raised to the power m plus k will be what? That will be simply m plus k plus 2 times m plus k plus 1 a k plus 2 and minus 2 times m plus k minus n a k equal to 0. And so here you can see this m plus k plus 1 times m plus k plus 2 times a k plus 2 will be equal to 2 times of m plus k minus n a k. And so you can write a k plus 2 will be equal to 2 times of m plus k minus n over m plus k plus 1 times m plus k plus 2 times ak. So this is the recurrence relation. Now, as you have seen in the initial equation, there are two roots and the values of roots are m equal to 0 and m equal to 1. So we will have actually two cases. In first case, we consider m equal to 0. when m is equal to 0, in this condition, what will be this recurrence relation defined in equation 3? You can see easily. So let us put m equal to 0 in this equation 3 so that we will have the recurrence relation for the case m equal to 0. So you can see this will be a k plus 2 equal to 2 times of m plus k minus n. But now we will take this m equal to 0. So this will be 2 times of k minus n. And over again we will take this m and this m equal to 0. So in denominator there will be k plus 1 times k plus 2 into ak. If you take the minus as a common factor, that is minus 1 as a common factor, then that will be minus 2 n minus k over k plus 1 times k plus 2 into ak. So this is the recurrence relation when m is equal to 0. Now from this recurrence relation we can find the coefficients a2, a3, a4 and so on by substituting the values of different values of k, that is k equal to 0, 1, 2, 3 and so on. So putting k equal to 0, 1, 2, 3 and so on in equation, in which equation? In equation 4. In equation 4 we get, in fact for simplicity I am again writing this recurrence relation so that we do not need to turn over the page. So you can see that this relation is a k plus 2 equal to what? This is minus 2 times of n minus k over k plus 1 times k plus 2 times ak. Now in this equation we will first of all put k equal to 0. So you can see when k is 0, then this a k plus 2 will be simply equal to a2 because k is 0. And in RHS you can see there will be minus 2 n because k is now 0 and over 1 times 2 and a0. And you may write it in this way. This is minus 2n over 2 factorial a naught. So this is the value of a2. Now we will put k equal to 1. When k will be 1, then a k plus 2 will be a3. So this will be a3 and this is minus 2 times n minus 1 and over 1 plus 1, this will be 2 times 1 plus 2, this will be 3 and here there will be 1, a1. Now you can write this expression in this way. This is minus 2 n minus 1 over 3 factorial a1. This is the value of a3. Similarly, now put k equal to 2 in this equation. When we will put k equal to 2, this a k plus 2 will be a4 and this a4 will be what? You can see this is minus 2 times n minus 2 over k plus 1 and k is 2. So this will be 2 plus 1, that is 3 times 2 plus 2, that is 4 and a2 because k is now 2. But we have already obtained the value of a2 here you can see. So substitute at the place of a2 this value which you have obtained already. So after substituting this value, this minus and here is already minus, so that will become plus. And so this will be 2n 2 times 2n times n minus 2 over 2 times 3 times 4, you may write also 1 here, and a naught. So you can see this is actually 2 square times n minus 2 over 4 factorial times a naught. Similarly, substituting k equal to 3 in this equation, we can obtain the value of a5. So let us put k equal to 3, and after substituting k equal to 3, we will get a5. And you may check that this a5 will be equal to 2 square times n minus 1 times n minus 3 over 5 factorial times a1. You may check it. I have not simplified this result, but you may check it yourself. So in this way, you can obtain all the coefficients substituting the different values of k. Now, if a1 is equal to 0, because you have seen when m is equal to 0, then it is possible that a1 may be 0. You can see here that a1 may be 0 when m is equal to 0, and it may not be 0 too. So if we consider that a1 is 0 when m is equal to 0, so you can see if a1 is equal to 0, then you may check that this a3 contains a1, so this a3 will be also 0. a5 also contains a1, so this will be also 0. So in this way, you can see all the coefficients with odd subscripts will be actually 0 in this condition. So then you can say a3 will be equal to a5, that will be equal to a7, and so on, and all these will be equal to 0 when a1 is equal to 0. But if a1 is not 0, because you have seen that when m is 0, then there are two possibilities: a1 may be 0 or a1 may not be 0. So if we consider that a1 is not equal to 0, in fact, in that condition, all the coefficients having odd and even subscripts will be actually non-zero. So in this condition, we will get a general solution. So if a1 is not 0, then you can see a3 will be not 0, a5 will be also not 0, and so on. So in this condition, we will write the solution in this manner. So in this condition, the solution of Hermite differential equation is given as, we write this solution y1. This is first solution, so I write it y1 instead of y. So this y1 you know will be what? This will be in fact a naught plus a1x plus a2x square plus a3x cube plus so on. And for simplicity, we divide this series in two parts, and in this way you can see this may be written as a naught plus a2x square plus a4x4 plus so on, and plus a1x plus a3x cube plus a5x raised to the power 5 and plus so on, plus dot dot dot. And now we will substitute the values of the coefficients a1, a2, a3, a4, a5 and so on, which we have just obtained. So when you can see, when we will substitute the values of all these coefficients, what will be this series? You can easily see it. So you can see y1 will be equal to a naught times 1 minus 2n over 2 factorial x square plus 2 square times n minus 2 over 4 factorial x4 and plus so on, and plus a1 times x minus 2 times n minus 1 over 3 factorial x cube plus 2 square times n minus 1 times n minus 3 over 5 factorial x5 minus so on. You can see we have simply substituted the values of the coefficients, that is a1, a2, a3, a4 and so on. So this is actually the first independent solution of the Hermite equation. Now we will see the second case when the initial equation has the root m equal to 1. So now let us consider the second case. Case second, when m is equal to 1. M equal to 1. Actually you have seen when m is equal to 1, then a1 is 0, and as a1 is 0, so a3, a5, a7 all are 0. We have already seen it. You can see here we have obtained this result, that when a1 is equal to 0, you can see here a1 is 0 when m is equal to 1. In fact, when m is equal to 1, a1 is 0 and a1 will be 0, then definitely a3, a5, a7 all will be 0. So when m is equal to 1, then we know a1 is equal to 0, and a1 equal to 0 implies that a3 equal to a5 equal to so on, and these all will be equal to 0. You can see. So we need only to evaluate the value of a2, a4, a6 and so on. And for this, first of all, in this condition, when m is equal to 1, first of all we will write the recurrence formula. You know what is the recurrence formula in general. You know this is a k plus 2. We have obtained this result. A k plus 2 is equal to 2 times of m plus k minus n over m plus k plus 1 times m plus k plus 2 times ak. Now, as we have considered m equal to 1, so when m equal to 1, then ak plus 2 will be what? You can easily see. Let us put m equal to 1 in this expression in RHS. This will be 2 times of k minus n and over k plus 1 times, k plus, not k plus 1, but k plus 2, because m is now 1, and times k plus 3 ak. And again, taking minus 1 as a common factor, you may write it, this is minus 2 n minus k over k plus 2 times k plus 3. You can see. This is actually the recurrence relation when m is equal to 1. And as you have seen, since in this condition a1 will be 0, and as a1 is 0, so a3, a5 all will be equal to 0. So in this condition, we need only to evaluate the values of a2, a4, a6 and so on. So to get the values of a2, a4, a6 and so on, actually we will substitute in this equation k equal to 0, k equal to 2, k equal to 4 and so on. So let us put here. Putting k equal to 0, 2, 4, 6 and so on in the above relation. When we will substitute these values of k, what we will get? You can see the first value, k is 0, so ak plus 2 will be simply a2, and k is 0, so you can see the RHS. This will be minus 2n over 2 times 3. And k is 0. So this will be minus 2 times, actually here I have mistaken here. You can see m plus k minus n is there. So this is 2 times of m plus k. Sorry, there should be, in fact, there should be also plus 1, because m is not 0 but m is 1. So this will be, when we take this minus as a common factor, then there will be minus k and minus 1, 2. This will be minus 1. So when we will take k equal to 0, the coefficient will be minus 2 n minus 1 over 2 times 3. So now substitute this value. So you can get a2 will be equal to minus 2 times n minus 1 over 2 times 3 a naught, and we can write it, this is minus 2 times n minus 1 over 3 factorial a naught. Now put the value of k equal to 2. So ak plus 2 will be now equal to a4, and this result you can see will be, you can check it, 2 square times n minus 1 times n minus 3 over factorial 5. You may check it. I have written it directly. You can check it. And similarly, when we will take k equal to 4, your result will be a6 equal to minus 2 raised to the power 3 times n minus 1 times n minus 3 times n minus 5 over 7 factorial a naught. And in this way you can obtain the value of a8, a10 and so on. But there is no need to write all those values. So in this condition, if we will write the solution of the Hermite differential equation, what will be our solution? You can see. So the solution of Hermite differential equation is, if we write this solution as y2, this y2 will be equal to what? This will be, in fact, in this condition, a naught times x minus 2 times n minus 1 over 3 factorial x cube plus 2 square times n minus 1 times n minus 3 over 5 factorial x raised to the power 5 and minus so on. This will be actually the second solution of the Hermite differential equation. Now you can see these two solutions. If you will see the solution of Hermite differential equation defined in this equation A1 and in equation A2, you can recognize that actually the solution defined in A2 is included in this solution A1. The only difference is that at the place of A naught there is A1. You can see here. If we replace this A1 by A naught, then you can see this second part of the first solution is identical to the second solution which you have obtained in this equation A2. So it is clear that the solution defined in equation A2 is included in the second part of the solution A1, except that A naught is replaced by A1. So in order that the Hermite equation may have two independent solutions, A1 must be 0 even when m is equal to 0. So in this condition we can write the complete solution of complete solution, not complete solution, but the first solution taking A1 equal to 0. So you can see that the solution A2 is included in the second part of A1, except that A naught is replaced by A1 is replaced by A0 is replaced by A1. So to get the two independent solutions, since the equation is of second order, so there must be two independent solutions. And so to get the two independent solutions, A1 must be equal to 0. So for two independent solution, A1 equal to 0. And therefore, if A1 is 0, then you can write the first solution Y1 will be equal to A0 times 1 minus 2n over 2 factorial x square plus 2 square times n minus 2 over 4 factorial x4 minus so on. You can see here. You can see this is actually, this part is of y1, because when a1 will be 0, the second part will vanish, and so the first independent solution of Hermite equation will be this much. So this is actually the first independent solution of Hermite differential equation. So the two independent solution of Hermite differential equation is now defined in equation A2 and in equation A3. So the complete solution will be actually the linear combination of these two solutions. So the complete solution of Hermite differential equation is given as y equal to a y1 plus b y2. Actually here a and b are arbitrary constants. You know, a and b are arbitrary constants. So this is the series solution of Hermite differential equation, and after this, in second lecture, we will see actually this solution of Hermite differential equation is actually known as Hermite polynomials, and so in the second lecture we will define Hermite polynomials and also evaluate some of the Hermite polynomials.